The next speaker is Daniel Luckhardt. He's talking on Kleisli liftings and decorated trace semantics.
Hello, so thank you very much for the opportunity to present our research here. So it's research together with Harsh Beoha, who is here, and Sebastian Küper. Yes, so let's start with something that is known, so feature transition systems. So the idea of feature transition systems is that you have to simulate various systems at once. So let's say you have an automaton that is somehow describing the process of booking a ticket. And then there are features that may be turned on or turned off. Let's say there may be the option to add a voucher or to have your ticket sent to your phone. But all these features are set at the beginning. So there is no dynamics. But now let's say that there are changes. Let's say that this feature of get your ticket on your phone is added maybe while the system is at the stage that some journey is in the cart, and at that same moment an update is happening. So we are adding upgrades. So and we will there assume some structure. So upgrades are coming one after another. So there is an order on upgrades, and we will assume that if one, so now the convention is if the upgrade is smaller, then it inherits all possible transitions from the previous larger stages. So to put that a bit more formal, we have a state space X and a set A of actions and a finite partially ordered set K that are called the elements of which are called conditions. And now for a feature transition system, that would be the configuration, each condition. And a conditional transition system consists of these data plus a transition relation, and it satisfies the axiom I just mentioned. So the lower the condition, the more transitions are enabled. Now, yeah, and just to recall, so this incorporates the traditional case of label transition systems where I just have where K is a singleton, and if the order is trivial, then I feature transition systems. So we are now looking at this extension where on runtime I can get upgrades. Okay, so as we are now here in the coalgebraic part of the conference, of course, we want to extend, view it coalgebraically, and what do we want to understand? How do we want, or why do coalgebras come in the first place? It's because one is interested in various notions of equivalences of such systems. So two systems behave the same way? There are different notions to do to describe that, and one of the most important notions is language equivalence. So language equivalence actually looks at each state and assigns to each state all possible traces. So all traces that some eventually end in some terminal condition. So formally, but I mean, there are other variations for other kinds of equivalences, but I will just stick for this talk to language equivalence. And basically, so what does it do? As I said, it assigns to each state, where is the light? Yeah, it assigns to each state some path, so some word in the alphabet A of possible actions. So it's a map to the power set, but a nice way to view it is to say it's a morphism in the Kleisli category. So basically, what we have here, we are now ending up with this coalgebraic map to a final object in the Kleisli category. And that's actually the nice way to view this from a coalgebraic point of view. So now we want, well, that was known. So now our question is, how do we transfer that to the conditional transition system? So for short CTS. Well, okay, so we actually Ash, Sebastian, and I tried a lot. Okay, so the idea is you have the monad over this machine endo functor, so A times X plus a singleton, and we have this final co-algebra morphism, and now we have to somehow plug in the K. So where could the K go? We could put it on the domain, but here, but this isn't quite sufficient because it should also appear on the right side. And also the theory doesn't really work. So we need something, when you think about it in the how it should look like, you want something of this type. K, so you have here twice K. And well, after searching a bit, we found out what it actually is. So this is the relative monad induced by P as the endo functor, so the power set monad over G, where G is this multiplication with K. So of course, now I owe you some explanations of what a relative monad is. So basically, a relative monad is the same like an ordinary monad, but it is a bit more, it is intertwined with another functor G. So in my presentation, G will be just an endo functor because it's the case that is relevant for us, but it's there's a more general notion where you have a monad that is valued in another category, but just stick to the simple case. So you have again your monad T, but that is now relative to some G. So for instance, your unit map does not go from X to T of X, but it goes from G of X to T of X. And the same, similarly, your extension operation is not defined on morphisms X to T, T of Y, but G of X to T of Y. And you have, like in the monad case, you have these laws where you add the G at the appropriate place. And now if you were very good, you notice that I define T only as an object map. That is because the rest of that structure, the extension, gives me exactly what it does on morphisms. So if I go this way and raise this, I ending up with a proper definition of morphism. Okay, and I can even do other well-known things. So I can define the Kleisli category. So the crucial thing now is happening here. So I have here the Kleisli morphisms are not of type X to T of Y, but of type G of X to T of Y. Well, okay, now of course the question is, are there nice examples or how do we get relative monads? So actually it's quite easy. So whenever you have an ordinary monad T and some endo functor, you can cook up a relative monad. You are adding that is defined on objects not as Tx but Tgx. And then you can adapt all the other structures. And now when you now do this relative Kleisli category construction of such a thing, such a relative monad coming from a monad T and an endo functor G, you see here that you are ending up with the right type, the type that I had on the previous slide. So G of X to T, G of Y. Okay, so now we found our theoretical framework. So let's see if we can now build up our theory in that framework. So actually now the problem is, I said, so these language equivalence is described by a final co-algebra in the Kleisli category. So what it actually means that we have to work in the Kleisli category. So we have to raise this functor B to the Kleisli category. And that is now the problem for the rest of my talk. There's a preliminary, so there's an easy case. So if we assume that this GB, so this G, by which we form the relative monad. This commutes already with the endofunctor B, then we are done because we can define this B tilde this extension in that way. But actually that doesn't work because, I mean, already in our example, so we had this functor B just multiplication with A plus an element. We see that these two expressions are not the same unless K happens to be the singleton. So that's not a solution. So we have to be a bit more careful. So, okay, so again, what do we want to lift? So we are mainly interested in a functor of this kind. Multiplication with our actions plus O, so for language equivalent, the singleton. And we actually now found out 3 axioms under which it's doable. So first so let's see. So first is G preserves co-products. So by this thing we can go from this guy to the guy here downstairs. So and then the third axiom is we already have that the Kleisli lifting works for this multiplication. So for this functor A in general. Okay, then we can go here and together with, so we can go down here. And again, with co-products, we can go upstairs. So there's this way. The only thing here left is, okay, we need this Kleisli lifting of A now. And now we have reduced this to this further problem where when can we lift this multiplication. So we basically got rid of the O. So, but before I come to our results there, just let me summarize what we can show. So now if this G preserves co-limits, we can prove that there is an initial algebra, and then by some known results of Wright, this also automatically gives us the final co-algebra, and this final co-algebra, I mean, that is what we saw. This describes our language equivalence. So, but now let's return to this A3 condition, so this Kleisli lifting. So, well, again, then it's well known that this Kleisli lifting actually corresponds to so-called Kleisli law. So Kleisli law is basically so now I will, because now I will describe a bit more a general theory where this B is a general functor. So I will call now the B and F. So this Kleisli law basically commutes Ft and T of F, such that these two axioms are fulfilled, this triangle and this pentagon. Okay, but perhaps it's more instructive to look at on it on the set case. So we call because in the set case we will see how what are actually the conditions we need. And in the set case, we know that in the set case, Kleisli morphism, so a morphism from X to the power set is actually the same as a relation on X times Y. And I will call this identification theta. And then we can do the same for cosets. So in the coset case, we end up with the relations that are downward closed in the first, upward closed in the first component and downward closed in the second component. Okay, and they can also, and these sets can also be described internally, actually. So by either the discrete, the 2-element set or the 2-element set with an order relation. So, and this turns out to be the right viewpoint to be able to do it for both cases, so the traditional unordered case in set or our CTS case with cosets. Or I mean, you could think about more general applications. I will say more about that. Okay, so for relations, so actually we are now have to view this functor P, this power set functor, in 2 different ways. Once as a monad and then also as a map to POS because there's this partial order on the power set. Okay, and we will also introduce a functor I. So I means in the set case, it's just the identity, but in the other case, it will form the, it will flip the order. So in that way, we can work with both cases at once. And then we can actually define this Kleisli lifting. It's by, well, just thinking of it as relations and using this phi and this theta to define, so this not var theta to define natural geometric entities, like here the element relation. And we can define a predicate lifting, so that is adding the set A. Yeah, and then also the direct image operation, and with that we can plug all that together and write down a theta that we need. And then we can in general prove that if this functor f, that is now just some ender functor, preserves weak pullbacks, then theta is a Kleisli law. And this works in both cases, set and POS. And actually the machinery we use to prove that is a bit more abstract. So because luckily I'm not the first one who is presenting more axioms than the audience can digest. So yeah, so we do it a bit more abstractly. So we have again this phi that goes to POS and that admits a pre-image operation. So another word for that would be a bifibration structure. And we have our I again that commutes with the functor f. And we also have this theta, this identity for this fibered approach. And we require two compatibility conditions. The first one is for composition from the right, and the other one is from composition from the left, and one is compatible with phi, and the other one, so the star means phi, and the other one is compatible with the direct image. And finally, we have our predicate lifting, that is a natural transformation. And under all these assumptions, if I would go back to the previous slide, you would see that all these definitions make sense. So thereby we can actually define our theta x. And now we can again define some very natural things. So let's say the diagonal, we can define it in terms of the unit, and we can also define a relation composition, and then one can define this predicate lifting. I mean, now it has to be, it's not the sigma itself, because the relation stands on two legs, not only on one leg like the phi. So, okay. And okay, then what we found out is that in the background there is actually one technical condition. So that is this instance of the Beck-Chevalier condition. So either you know the Beck-Chevalier condition, or you just accept that this is what you need. I mean, it basically means if this diagram commutes, then you also have that this diagram with the pre-images. So you can apply phi and then this diagram with direct images commutes. Okay, so and when we assume this Beck-Chevalier condition, actually everything becomes quite a nice geometric picture. So we need this triangle to commute, and this means that this lifting operation here preserves the diagonal. So the diagonal of x is preserved to the diagonal of f of x. And this pentagon law means that this relation composition is preserved. And well, perhaps, I mean, that was a lot of definitions, but we found out that it is actually quite advantageous in the way that if you check it on an example, then these criterions are, well, easy to check. So you have to digest a lot at the beginning, but then it turns easy. And also it's interesting in view of later applications we have in mind, like if we enrich the transitions, let's say with probability, you do a transition with a certain probability and so on, you will end up in categories that are maybe a bit different to set. So then that general machinery may prove very useful. Okay, so perhaps some concluding remarks now. So we were able to treat both the set case and the post-set case in advance by introducing this functor I and some list of axioms, and we were able to describe this machine endofunctor. These assumptions are easily checked, and if for the set, if I set O to the singleton, then we give language equivalence for LTS. Sorry, for CTS, so these conditional transition systems we are interested in and that are new. But we are also able to define ready equivalence. In that case, you have to replace the O by the ready pairs, but actually failure equivalence turns out to be a more troublesome. So you can, well, it works if you view it as sets, but if you really want to include this order structure, it turns out that it is flipped. So in that sense, our machinery does not apply. And we also worked out that it works with some CPPO enrichment. So you can put more structures on the categories. And as I said, we are interested in future research in putting more structures on the transitions, like probabilities or even, let's say, weights from a semi-ring and so on. So then, thank you very much for your attention. Yeah.
I did not get what you end up with as an equivalent between CTSs. What is the formula for what are the equivalent?
If these this morphisms to the this final co-algebra morphism agree.
And does it mean that the MFPS that you get by restricting to some set of conditions are always equivalent?
Sorry?
Does it mean that when you restrict your CTS to one MFPS by looking at the particular set of K, subset of K, and then you look at the language equivalence for each of these subsets of K, you always get the same?
You mean subsets of this blackboard K? Or?
Yes.
So what you say, if I look at every subset of the K, as you say, if it's equivalent for every subset. I think that should be true or
I think for set, it is the case that for a fixed case, the clearer for a fixed condition, the language is and this is true for all. But if you are into process, then you have to do more than this. In particular, for each case, fix a case, and for every case below it, the language would be different. So this filtering argument is not there in set, but that's the main.
You said at the start, I think, that you're assuming that when you do an upgrade, it enables more, but preserves the existing transition. So there are some systems I can imagine where upgrading disallows some things, like, for example, airline reservations. If somebody books a seat, nobody else can book it afterwards. Can you handle that? I didn't see in your presentation where the monotonic property about upgrades played a role. Where does it play a crucial role?
Yeah, I mean, otherwise you would, I mean, the question is, you would get funk. I mean, you could still say, okay, to where it a good question. So where does this, okay, so I mean, it would alter the monad basically, because I mean, this would be another monad. Would it partially, yeah, I mean, it's basically this no, yeah,
I think
before, yes, here. So yeah, so you would end up here with something else. Yes, flip. I mean, it should be more. I mean, then you are basically back to the set case where you just, I mean, then it's like that, but you have somehow additional information lying around in which stage you are. Yeah, I mean, perhaps it's possible to adapt that. Yeah. Yeah.
Kind of historical question. You started by talking about relative monads as
Yes.
opposed to pure monads. Who created the notion and why?
I think relative monads, this term was by Kirchberg in the last decade, but I think, Harsh, you found this paper of these guys with relative junctions.
so
That
actually,
was by Ulmer, I think. But then Kirchberg, I don't know if Kirchberg was aware of that or rediscovered it on his own, or.
I think the point was to the junction. So there's a working on the nature and then
Yeah, okay.
and computer science, we found the reference was the paper by Austin.
Couple of examples of the fact that achievement fits in the picture. You said that the conditions are easy to check, but are true.
Yeah, I mean, we checked it for these two, so it's then here flipped.
So for example, the last slide you actually did the new way. So what is the fact that achievement? How would it check if we want to trace equivalence?
I mean, in one case you take the ready pairs, and in the other case the failure pairs. But where's it? So the G is this multiplication with A. I had it on one of the first slides. So here.
Yes, that's the G as well. Is there anything else?
Well, I mean, basically, in the general case, it only has to fulfill these axioms. So you could, for instance, let's say, take something like in a multiplication in a monoidal category should work, or I think it basically, as long as it assumes these A1 to A3, it works. So you could think of something else, just being a bit creative about what what you would consider. I mean, I mean, for the applications, it's a set of actions, but perhaps you can come up with something more fancy.
Question?
Your axioms that you introduce, plus the directional division, was very much like a doctrinal structure, like a fish thing. It's like
so far, it sounds very interesting. Yes, I should look into that. Yeah, I did not make that. Yeah.
Thank you.